And I actually just published a new version this morning with just some changes, minor changes, just in case we need some. So we'll see. But
so it just broke. Yeah. So I played a bit. I did it. I rerun the tutorial. I modified it a bit. I told you I got it to expand forever somehow, or at least
yeah,
I think it did that. So I played a bit. I'm not starting completely from scratch, but yeah, as I said, like the biggest challenge for me is like the rewrite logic. I mean, should be simple. We even have something like that. Is more like exactly what kind of stuff we need to represent in like the level of representation. So I will tell what happens in PyTensor.
Okay. Yeah, that sounds good.
Tell me the zoom if you want a bit more or less.
That's fine. Yeah.
So we have variables, which will be dummy inputs. You can give them values later when you actually evaluate some expression. We have constants, which can be just NumPy numerical types. Everything, well, I'll show you later. And we have, let's do something with this. Let's do that. Okay, so have that. We have a debug print that just gives an idea of the structure of the things we have. So, and then I will show the actual objects we have. So we have a multiplication between x and 5. Yeah, I can show something we also have, which is not so, it just shows how it's built. We have repeated stuff. So a lot of the things we do in like the optimizations we do, we just merge identical expressions, which is not something that happens in Egglog, because when you build it, it's already going to be.
Yeah, exactly.
Yeah. So, but that was just to mention that we do have duplicated stuff, and then we spend a lot of time just merging it. So it looks like that. Then I can print everything as specific like types. Everything is well.
Okay, cool. I was going to ask about
because
that.
This is a fork of Tiano. I don't know if you heard about it back in the day. So everything was like geared so that you can compile a function to efficiency code. So everything was like nicely statically typed. So we know that we have a scalar float 32. This is the constant. Scalar float 64, shape 0. And multiplication also, we get the type immediately. Because so I could make a vector if it's a vector. And this is the first like thing that starts being specific. Which is, okay, two things already. Our input is a vector, and it has a static unknown shape. So we always know the number of dimensions, that's static, but we don't know the shape or the length of this dimension.
Yeah.
Okay? We can provide it. That's something we added since the times of Tiano didn't used to exist. So you could say that it's 5. Then it has to be 5, and it can assume it's 5. And actually, you see that we already do some eager like type inference. We already know that this multiplication is also going to be 5. Because one of the inputs is 5 and the other is 1. It's going to broadcast.
Yeah. And you have the expand dimensions for the broadcasting.
So we never have so the broadcasting is still done implicitly by the multiplication, but we always have inputs with the same number of dimensions. So if something has less dimensions, we use these expand dims to make a scalar into a vector in this case.
I see. Okay.
And there's one tricky thing about here, which is for broadcasting to be valid, it has to be non-statically. So if you have, let's take away the constant. So the constant, we always know it's static steps. So that's not interesting. So if you have something like this, okay, then you do the graph. It's going to say the shape is 5, but importantly, it is x has to be static. It cannot be a shape of 1, or there will be an error raised when we evaluate it. Okay, so we cannot like dynamically, or you cannot dynamically broadcasting. That's how we call it. So something that was not known to be a broadcasting operation to happen. So I can do it by the val x equals this, y equals this. It's going to complain. Let's see. or it should. I don't know if you have the right person. Let me see. Shape. Oh, okay.
Yeah, the shape is not
I
compatible.
probably,
yeah.
I think, no, I think I just, yeah, it shouldn't happen here. I don't know why it's happening here.
Because it's saying that X is.
Yeah, let me give the right. Let's
Okay.
see what broke it here. Yes. It should be imported by default.
Yeah.
Okay. Yeah. Okay, so let's see what happens if I need one. Yeah, this is, I think, a slightly older version. We have a better error message nowadays, which is something like, yeah, something like runtime broadcasting is not allowed. So this is not allowed, but if you told it, it had a shape of 1 from the beginning. So this is
yeah. Yeah.
So you told him that it should be happy. Okay.
Yeah.
Then he's happy about that.
Okay.
And the user can also, as an operation, say, okay, actually, even though I didn't say from the beginning, this has a static shape of 1. So then it's also happy.
Yeah.
Should be. I don't know if this, yeah. Okay.
And basically the so how does like here you kind of define some expression with variables and then you evaluate those variables with certain values that gives you back a result. Is that the usual like flow, or like how is this used? How do users use these features, I guess, is the question.
Yeah,
they build up a big graph like this and then
they build a graph. For instance, the main user of PyTensor nowadays is PyMC, and we are developing both, so it's the same maintenance.
Yeah.
So we use PyMC to build like a log density graph so that we can sample MCMC. And we also use PyTensor not for the log density, but also for the gradients. Okay, so one of the operations you can do once you have a Z variable is just ask what's the gradient of Z with respect to X. So it also has uplift. Yeah. So everything is a graph, and then once you have the whole expression you need, the graph is to be scalar. Okay. Once you have the whole expression you need, you compile it. Usually eval is just for debugging, because every time you compile the function, the proper way to do is a PyTensor.function. And as you specify what are going to be your inputs, what's going to be your output. So that's it. And that's where nice interesting things can happen. Like if you have multiple outputs, you can share computation if there's like shared stuff between the two.
And then this.
So I'm gonna make it show our optimization under the hood. It's gonna be a lot of every like single rewrite that's applied when you compile. When you compile the function, we run a whole pipeline of rewrites. Stuff like canonicalized and put some things to like stabilize operations, like put a log1p if you have a log1 plus x, stuff like that, or specialize if you have a dot. We put some BLAS operators instead that users don't usually work with. So you have some very not so nice, but they always say, so there's a rewrite, which is just a couple of lines of code and says we replace a node with another. Okay. And then we can see what a compile function actually looks like. So in the end, we have something a bit more specialized. So this is giving us z and the grad of z, to just the addition of x and y. And the log is a NumPy full. So we're just multiplying x by y. The specified shape is still there. And the gradient is just filled with 5s, basically. You figure out that. Does that make sense?
Yeah, and then
it's broadcasting the y. Yeah.
And this function,
broadcasting the y.
if you like it has this abstract representation here, but like if you call it,
Yeah,
is
now
it
it already
doing a
detects.
similar kind of like eval thing, or does it do code gen?
Yes,
or
if it's the other way around. The eval kind of pulls the machinery of PyTensor function under the hood and then evaluates the numbers we passed. But
I
if
see.
you are, the idea is if you are in production, you compile one PyTensor function and then you can call it multiple times. So it's kind of like the equivalent of the number JIT is pay the cost once, and then I'm gonna reuse these multiple times.
And when you call it, like, do you have your own basically interpreter that goes through each of these expressions and calls it?
Yeah, so the original one is like running C code, so it has like a virtual machine that takes care of like putting stuff in buffers. But we actually get moving away from that. So for you, we are familiar with number. We can say that we can actually compile to number, and then we have one single like number function under the hood, and we just pass the inputs.
I see. And so does this do Python code gen of like Python code to pass the number, or does it generate number IR directly?
No, we do a mix. We do a mix. We do a lot of like string that then gets evaluated, and we do some like low level, like for the LM-wise operations, we write directly in whatever, like in the low levels that are available from number or the dependencies number use.
Interesting.
So
okay.
Just this. Yeah. Okay. So that was to give an idea of the types. So static types is that.
Yeah.
They have to be, basically the information it has is the D type and number of dimensions. It always has to be non-static, but the length of these dimensions can be known, an integer, or none if it's not specified. With that weird rule, if it's none, you cannot broadcast at runtime.
I see. So yeah, dimensions are known statically, but the shapes can be none. Can be unknown.
Yes. And that's already one of the things we don't like, is that there's already a mix here. Like we have to do some like eager shape evaluation when we create the node. And there's a lot, and there's I will mention later, there is like, you can also evaluate the shape of a graph. That's almost the same code, but it's supposed to work symbolically and doesn't have nuns in it. And it's also something that we probably want to find a nicer thing than what you are doing, because it's just repeated code. So yeah, I said you can compile it to number. Actually, so scalar, Z, I didn't define the gradient. Yes, so this is always calling, it's always calling PyTensor function under the hood, so you shouldn't be doing this all the time. 1 times 1 is not a nice gradient. Yeah.
I see. Okay, that does the function. So I see, but when you call this PyTensor function, like these ops used to be evaluated by a C backend, or they still are, or sometimes?
Now, yeah. So there's a default. There's like a global flag that says that's the default backend. It's still the C, because we have like everything is supported in the C, whereas we have 2 alternative backends, which is number JAX, and those have like
are not
90
all supported.
Something. Yeah,
I see.
Coverage. Yeah, but
so to get to the C backend, you basically have to. It's familiar with this syntax of expressions and everything. This kind of Interesting.
But cool. As I said, we are moving away from the C backend because it's a lot of maintenance overhead, and there are better tools now that are doing low level compilation.
Don't have
so we don't want to reinvent the wheel.
Redo all of that. Yeah, that makes sense.
Okay, so we have that. The other thing we have, so I can show what that graph actually looks like. So this is so everything is a variable type. So Z and the inputs also. Okay. And then they have a thing called owner, which is the node. And there's a picture. I can maybe show the picture first. Graph structures. Just like this. Okay, so it looks something like this. Variable as a type. So in this case, it's a matrix. It also has a D type. It has an owner, which we call an apply node or a node. This has an op, which is like the operation that this node performs. And the apply has as many inputs as this operation needs to compute the output. And could have multiple outputs. Some operators have multiple outputs. And then it just goes like that to the root.
Yeah.
So yeah, we have this.
Yeah, so it's just kind of like a nested tree, basically, of ops and stuff. Yeah.
Okay. The thing we have the op, which is the important thing. So the op LMYs is like the universal function in NumPy, so something that can take arbitrary batch inputs and it's going to do an LMYs operation, like a basic LMYs operation. In our case, it's an addition, so it's all okay. It has a multiplication. And we have the inputs, which it's a list, so it's a very interesting type. Which would be x, y, and these would be variables. And the root, the only thing that happens to root variables is they don't have a owner or a node, so it's none. If it prints none ever, okay. That's what happens in a root variable.
Okay.
That's kind of the structure. And when we do rewrites, what we do is, and it's actually important that this is a list. When we do rewrites, like we basically change the. I think that's what we changed. We changed the. When we have a node, we change the variables that go as inputs. So if you have if you have an output, if your output is pt.log 1 plus x, and then there's a rewrite that eventually is going to do like is actually x. So it's going to rewrites do. They mutate in place the list of inputs.
The inputs. I see. Cool. Yeah, that makes sense. Yeah, so I'm thinking about. I feel like there's a couple ways to try things out, I guess. I'm just spitballing, but one of them could be to so like in the array API, like we could make a interface that works similar to the one you showed, basically. And because basically there's like a little, so or we could, like, I guess the question is there like kind of like an MVP or little example that would be helpful to kind of drive like a small fake implementation, to see like, how does this work? Because we could just start implementing all this, but I think it would be helpful maybe to have like a
goal, like
a little goal. Yeah. Even if it's tiny, like, I don't know, adding two things and seeing the shape statically, or I don't know what it is, but or if it's like, hey, there's a particular complicated rewrite that you can't do currently, or it's kind of messy, we could try to rewrite that rewrite in this form and make sure that.
That would be nice. So I think there's a nice one, which is the one I mentioned to you. So let's say we have, okay. Tensor is the general one, so we can, I can just say the shape can be arbitrary. So let's do that one. I think that could be interesting. So that's one that we don't have yet, but I want it. It's not particularly difficult, but I think it involves all these like concepts that are a bit idiosyncratic about PyTensor. So
cool.
Okay, let's say we have none by none. So we have a matrix. And we have how is a column matrix. Okay. Yeah. That's a column. Yeah. We add them up. No, we multiply them. And we sum them along the last axis. This is our output. And we want to rewrite, or even if not to rewrite, that's another thing we want to do with the Egglog would be not even just for rewrite, but just to like ask if an expression is equivalent to another, right? Which is
yeah, a test to check equivalence.
So it's enough for us if you can find that it's equivalent to X. That would be this equivalent. You see, I didn't complicate the example too much. Summing along.
So yeah, I always get
the last dimension. Yes. So this should be equivalent to these or something like that. We can evaluate it.
Yeah. And
but not equivalent to which one? Let me see. Yeah, axis equals 0. Because in this case, y would again broadcast. Sorry, this should be equivalent to pt dot dot squeeze. So we take that dummy dimension of 1, right? Which would be killed by the sum operation. It wouldn't be equivalent to this. Right, I think.
Okay.
Just out of the wrong.
Let me just, I'm going to draw this out because you're
Yeah.
obviously much more, spend more time thinking about tensor math. Let's see. So you have the first shape is just on multiplying those.
Oops, sorry for that.
And so the first, oh yeah. Okay, cool.
Let me see. First this matches my expectation. What is it? Okay, it's an old version that didn't allow you to specify it manually, but okay, doesn't matter. Okay, so let's see, I didn't mess up. It's basically a mix of how do you say associativity and tensor shapes. So sometimes you can assume them, otherwise you cannot.
Okay.
See if I messed up. It's live.
Okay.
It's always hard to live, you know.
Yeah, definitely, especially when you're doing multidimensional tensor math.
Yeah, I already messed up something, did I? Maybe I already did. But they are not compatible already. The one I thought would be equivalent. So what was I trying to do? Sum along the last one.
And -1's the same as 1 here, right? It's coming from the.
Yeah. Let's do that.
Okay.
Yeah.
Okay.
Yeah. So I think this would be the. I thought it would
So
be the
summing. So for the out, the shape will be just a column basically again. Is that? No, I guess it'll be, yeah, it'll just be one. It'll be one dimensional.
So, yeah. It's a vector.
A vector. Okay. Yeah.
So what did I mess up here?
And that.
So this is a vector. And y was is complaining.
Oh, I see. Because the sum, you're saying because the sum is just summing one item.
Yeah, I messed up x and y. So
okay.
Yeah, that was stupid. Yeah. Okay. We put in other order because it makes no sense on x, y. Yes.
Okay. And your letters are switched now too. Anyway, that matters. But the names of them on the first couple lines. X and Y are reversed.
Yeah. X. X. Okay. Perfect. So now let's see if the equivalent one is working. Nice. And then not
Okay,
equivalent.
cool.
Hopefully, which were they complain? No. Yeah, it's not. It's probably already incompatible. Yeah.
Okay.
So
okay.
It's not right.
Yeah. Okay. Let me just make sure I'm. Could I go through with you to see if I'm following?
Yeah.
The math. And I think you said x equals pt.tensor y. So just I think those are the letters are switched. Not that it matters.
Matters if you look at the graph. Yeah.
Okay. So you're multiplying and then you're summing, and so this one you're summing x. Oh, it's just the okay. So you're trying to. I see, like the.
Okay. So okay. Let me start. This is the one that's not supported right now. The one that's already supported in PyTensor would be this one, which is a scalar. That's simpler. Right. So in this case, you can always take the y out. Okay. It's just a. It's just a scalar. So either you multiply and then add, or you add and then multiply.
I see.
Right. So that case we support. Now, if y is being broadcasted in the dimension that's reduced, you are still in the same case, except you are like, you have a vector kind of associativity instead of having a scalar associativity, which is what this is doing. And also, maybe it's more. We are more used to that, so let's do that. So this is the case that's allowed. This is the equivalent, and this is not allowed because what we are doing here is basically mixing dimensions, I guess, right? The x is going to reduce this dimension, and then we would be trying to multiply with this dimension. So we're trying to pair this with this. And this would be more obvious. Like if we try like this, it's already going to give us immediately a shape error. Because now, like if we try to do this, it's already complaining. Depending how, it's already not static type that 5 and 3 are not.
Okay, this seems like a good example. So basically you want to say, hey, can we prove that these things are equivalent, but it's not equivalent to this other one?
Yeah, exactly.
And I'm trying to think and when you're thinking about the rewrite rule, like besides kind of, I mean, I guess we could push it down all the way, basically, the value. Like, I guess, is there a way that you have of thinking about this rewrite rule? Or we could try to just make something up, but.
Yeah, so the way we do this rewrite rule, I have a pull request for that, is we basically, we check if any variable. So first, okay, the way we always do in PyTensor is we check if there's a sum operation. Then we check if the input to that sum is a multiplication. And then we check if any of, and actually in PyTensor, this is, actually the multiplication could be in a variadic form, but we don't need to worry about that. So we check if there's only 2 inputs. And then we check, does any of these inputs have a dummy dimension along the axis we are summing? Or actually only dummy dimensions along the axis we are summing. We always know about dummy dimensions because I told you that if you have a multiplication, we always going to add this one even if it was not there.
Yes.
So even if you did it like this, by the time you look at these, there's going to be an expand dims that puts this one.
I see. So basically whether the expanded dims is 1 along that axis.
Yeah. If it is along all the axes, and yeah, we didn't have an example with more dimensions, but we could have axis 0, 1, and there could be more. Yeah. If it is, then we know we can take it out. We can sum whatever is inside the same way, and then we multiply after we kind of drop the dummy dimensions. That should be equivalent.
And yeah, okay. Basically, and to drop the dummy dimensions, does the squeeze just drop?
Well, this is, I think this, if you call PT the squeeze, this is an old stuff that we changed. You can be explicit about
what you're access. Doing. I see.
Sorry, axis 0. By default, it's going to squeeze all the ones that have a static shape, but that's not relevant for us. By this time, we're already going to have a graph with it. Okay.
Okay. That sounds good. So,
and maybe the last thing that I could mention is exactly what this op looks like, the ones we are talking about. What is your problem? Squeeze. Unexpected.
It's
okay. Sure. I'll probably change something here. This should be. Did that upset you?
Squeeze access 0. Yeah.
Yes, it's good. X is 5 by 3, 5 by 3, 1 by 9. This should be 3 by 5 now. That can work. I changed it to be left because I think it's maybe more intuitive. Okay,
cool.
So I showed you the LM-wise what the XY looks like. The out I didn't show, but it's a sum.
Yeah.
The owner is this node that has as an op. So it's a fancy op. So like we don't have just a sum, we have this. It's a reduction operation basically. And it has what is the scalar form of this operation, which is an addition, right? Summing is just a bunch of additions. It has the axis statically known, 0, always in always normalized to be positive. And that's what we need to know. So this is how we could know what kind of state it is. And the other one that takes here, well, actually it doesn't exist in our case, so we don't need to worry about it. But if it existed like this, yes, it's going to combine. It's going to be this the expand dims here of the y. So we have the multiplication, which our dimension is an LM-wise. Like that. It's a universal function. And the inputs, the y in this case, is given automatically.
And
you didn't even. Okay. Okay. Perfect. It's a expand dims operator. That's the only other one that we might need to know about, which is a dim shuffle, which basically allows you to. It's a more general one. You can reorder any dimensions, and you can add ones. It shows as like this is a static. Basically means we add a dummy dimension, and then it's the first dimension of the original input.
Yeah.
Cool. But for this
right
now, we don't need to worry about that.
Okay. Yeah, and maybe for the rewrite for now, maybe just without assume that the shapes are already broadcasted or whatever, just to make it simple. And so if we were going to write the rewrite, you're just saying it's sum of x times y with an axis is the same as summing x times removing that axis from y if that axis is a dummy axis of y. Yeah, which is basically that. Cool.
You wouldn't remove y otherwise to begin with. But
so one way, so we could either try doing this rewrite on top of the existing ND array test implementation I had, or just build a new tensor one.
I was inclined to building a new one just to have an idea,
Yeah,
because this
that
is the
sounds
part I
good.
don't quite get, like, because I started mixing stuff that already comes pre-built, like the vector.
Yes.
And then I wanted the length of the vector, and it was like, you are mixing stuff that you shouldn't.
Yes, yeah.
I don't have,
Yeah,
that's really where my
the built-ins
blind.
are a bit confusing at the moment too. Okay, well that sounds good. So let's
What?
yeah.
Yeah. What objects do we need to create here?
Okay, so we can start by making, and we can, for now, I guess we could keep the same requirement that we know the shape statically, even though we don't necessarily need to keep that requirement with Egglog, but we can just keep it. I mean, not the shape, the dimension statically.
Okay, yeah, the dimensions we can keep the requirement. Do we want to have something like this from the beginning, or it's too much?
Yeah, that's fine. No, that's fine. So let's start with you kind of have to start from the very beginning. So we'll start from we'll just make an int class. So there's like built-in int 64, but those all have to be basically eagerly evaluated. They have to be known on construction, basically. So we always kind of want to write wrapper classes that that lets us build up like an abstract integer.
Right. So let me just open the where I was just
reading the tutorial. So you can see I save some.
Yes, yeah, the decorator thing. Like
yeah. There's. I think I want to. Hopefully, I'll make it a little simpler soon. But for now, that's what we got.
That's fine. So we'll have something like this, right?
Yeah, exactly.
Okay, so we have an graph. We're gonna have what would be an int, right?
Yeah, I just called it int.
Yes. For now.
And you could maybe just keep. Yeah, I guess let's see what we'll need. Maybe. Yeah, I guess you could get rid of all of them. Maybe just keep the var, because maybe we'll want to.
Yeah.
And
everything else is okay. So we use.
Yep, and then the var it should return int. Yeah.
Perfect.
Yeah.
Okay.
Okay. Cool.
Then I guess we have a shape. Or
we have a shape.
Or do we have a type? Shape.
No. Yeah, you'll have a shape type. Yeah.
Just to show. This is what the type looks like, and this is how you initialize it.
Yeah, so we can have for shape. So this is another place where there's no variadic functions currently, unfortunately.
Yeah, I noticed that.
Yeah, so that's definitely a sore spot. But so we can just have a shape, and then the way I've been doing is you kind of just make it like a linked list. So you'd say like there's a constructor for empty shape, and you can add two shapes. That's really how I've been doing. Or constructor for a shape with one element, and then you can add two shapes together. So you can just call it shape, I think, because it will be maybe static, maybe not.
Okay, it's just I'm thinking already ahead that we have these two things called shape. But yeah, okay.
What are the two things?
Well, there is this thing that allows integers in nuns, and there is this thing, which is a symbolic shape, which is like a variable that you can make a graph of. This one, there's no nuns in this idea, right?
Yeah. That's a good point. Actually, so in I have both of these in the. So actually, I call them either way. I call it a tuple of ints, or you could call it a shape, and then I call the other one like there's optional tuple of ints or something like that. Basically you need two data structures, one that can have only ints, one that can have nuns or ints, right?
Yeah. But for now we're not playing with this one yet. So
so
okay.
Yeah, I see what you mean. So why you did static shape? Yeah. Yeah, so you could call it either way,
or type
whatever
shape,
you want.
maybe type shape. Okay.
Sure.
Yeah, tell me.
Oh no. So this is the one that can only take ints, or could it take ints or?
Yeah, ints or nuns.
Ints or nuns. So then we want another. So you could have two constructors here. you could have one that's called, so I'd make these as class methods. I would say one is none. You could just call it none. And it takes no args. Or it takes the class, I guess, and then returns this type.
Returns the class?
Type shape.
Or it doesn't have a...
Yeah.
Okay.
Yep, and then there's yeah, you could make it the init is fine. That takes, or
Okay.
another class method, either way. You could just make it the init, I guess it's a little easier. And then that takes the, just a int. Well, along with self, yeah.
Yeah. Access. So that would return also itself, right?
Well, it
These we
return
are saying
none.
it has to be...
Just
yeah,
because inits return none, but
yeah.
yeah.
Okay.
Yeah.
And I need like probably
Yep.
here.
Yep.
Okay. So right now we are restricted to the vector case, right?
Mm-hmm.
Because we cannot do this.
Exactly. So then what we can do though is we can add like a dunder add method to the type shape. And just say that that's how we make.
Important right now, but I'm gonna need this soon enough if I want to play more with it. So this would be self and other.
Yes. Other
shape.
Yeah, exactly.
Okay, other, which has to be a type shape as well. Do I need to do anything with it, or no, you're gonna do it the fancy way, which it's gonna be with it, right? Okay. That's
so it'll return, yeah, the type shape.
Type shape, yeah. That's so cool, you know. That all the operations are also like represented symbolically.
Exactly, yeah.
Yeah,
it's nice.
Okay.
Cool.
So if I wanted to make, and we need a D type, but for now let's just say everything is integer.
Sure. Yeah.
Yeah. Because I could pass 2 arguments here, right? It just cannot be variable. I could have not here when we okay. We should create a type.
Yeah. A tensor maybe? Or you were saying
tensor type. Yeah. That would be equivalent to this thing we call the tensor type.
Sure.
I think, right?
Mm-hmm.
Or I don't know. So we have a distinction. So we have types.
I see you have a tensor
variables.
Type. Yeah, I would just make a tensor.
Types. Okay.
And
the tensor, what does it have? Type shape, I guess.
Yeah. Yeah. Yeah, we could make a constructor that takes the type shape and also maybe a name. So this is there's other ways we could do this, but for now I think, and the string should be a.
This it's not gonna like it.
It should be a string. If you type string like capitals.
Okay. It is autocomplete, but I imported everything.
It says the string, the full word like.
Okay. Okay.
Yep.
This should be an expression as well, right?
Mm-hmm.
Okay. The other thing would be an operation. Is that also represented as a class itself?
Operations, they can just be functions. So
okay.
Like which ones do you have? You have, well, you have multiplication, which can be on the tensor type.
Yeah. I was so the reason why I was going for the operator is because then it would be easier to map, because everything is a operation in a PyTensor.
Like you could do the sum and the multiplication together, like as an operation, is what you're saying.
Both of them like would be an operation. Like so, I would.
So one way, and then, like one way you could do it is, you could add the sum and the multiplication, but then also add a generic like op like a binary op function that takes two tensors and an op, and then the op could be sort of like basically an op. It would either be multiplication or addition, like a enum, basically. That says. So we could do that so that.
Well, yes. So we
and then
have
translate
actually
one to the other.
So the way we actually have to so you say like what the way we merge equivalent expressions is if it is the same op, and the same op basically it has these properties that if they are the same, like the two instances are the same operator basically. Let me just see how we call that, props. I just never know what it's called. So. One underscore.
Yeah.
Maybe. Then can I call it? Perfect. So it's a tuple. So this tells us, so this would be another op. It's the scalar op. Doesn't matter. It could be a string for us. It's the axis, and these are things that don't matter for us. But basically, if two operators match on these properties and they have the same inputs, then the output is the same. They can be merged.
Yeah, that makes sense. So in our case, what are all the ops we have? We have addition, multiplication, and we also have a sum function, right?
And we have a squeeze.
A squeeze.
Operation. Yeah, that's four.
So
multiplication.
Would sum? Yeah.
No, just multiplication, sum, and squeeze, right? That's the only.
Oh yeah, no addition, right? Yeah, I guess you're right.
No addition. Well, the addition is kind of given by the sum.
Implicit. Yeah. Okay. So I think for now we can start is just writing them high level, and then we can decide if we want to rewrite them as like a more generic op. Does that make sense?
So what is the high level? Is
so
it a
just
function? Or is it a method?
Well, if we want we have multiplication as a method, so we can just make a mul method.
To see both ways anyway. So if I understood correctly, is it something? Right. Okay.
Yep. And then the sum and the squeeze can both be functions. I mean, they could be methods. Either way, it's really up to you. You know, it doesn't really matter. They're kind of the same.
Is it a class?
So it's a dot function, and then that's the just a decorator on a function.
Why is this not called the graph dot expression?
Yeah, I was thinking of actually just removing this expression class and also removing the dot class maybe, and just doing @egraph for both of them, just so you have to write less. I don't know what you think of that, but
you can inspect the type here. That would be nice.
Yeah.
Okay, so let's say sum. Now this one you'll have to guide me.
Okay, so and what's the sum? It just takes one
input, and it has static axis. Yeah.
And it has an axis. Okay, so the first one can just be whatever you want to call the array, X or array or tensor or whatever, and then type tensor. Yeah, and then the axis equals. So that's this. You just want it to be one int. You could just call. Yeah, you could just do int. The uppercase.
Yes, the general one would be that.
Okay. Well, do you want to? Maybe we start for now with just a single axis.
Yeah, let's do that.
If that works, and then we can.
Sure.
And you can. And you can just make it our special int class, capital int.
Okay.
Yeah.
Sure. Not that nuns would be allowed. Well, yeah, we don't allow nuns. We convert them, but sure. Yeah, that's fine.
Oh yeah, our int doesn't allow nuns, I don't think. Right? It's just or well, the var is not a none necessarily. It's like a abstract.
Sorry.
It's like a. I guess I see what you mean. Yeah. Anyway.
Shouldn't these? Okay, I got confused. Yeah.
Oh,
Shouldn't this be a union? No, we create nuns different. Okay. So this is not.
Well, actually, do you want to go back to look at your expression again? Because I want to look where you're at the top where you wrote it out, the example. Yeah, here. Because I'm trying to look again at the none question. So here, I think these shapes will be there'll be vars, I think, in our case, because we want them to each be separate. Like if we say that, or I think that's one way to do it. Is just say like, hey, this is the first dimension of X. This is the second dimension of X, etc. So in that case, I don't know if we'll need this like optional shape thing, because all the shapes will then be integers. Some of them will just be unknown at compile time.
Right. And the one thing we do in PyTensor, which is if you have an X plus Y, and we do, I mean, they wanted to do it. We haven't done that. If you have like this and you add the two, and then you ask the shape of X, we take the liberty of saying that if this was a valid graph, this dimension has to be the same as Y.
So then you know the shape.
Rewrites where we can assume the shape is the same if the two things are in an LMI's operation. Otherwise, the graph would be invalid. And that's another reason why we don't allow the dynamic broadcasting, because then our rewrites would be invalid.
Yeah.
Okay. So I guess what I'm saying is, if it's something with a name, then we could say it's the same, right?
Yeah, exactly. So yeah, I think for our type shape, like we don't maybe even need the none class method. I don't know. We'd comment it out maybe for now and see, or whatever, delete it. It's fine.
Okay, because we can just say it's a int
with a certain name. Yeah.
Or a variable integer. Yeah, perfect.
Yeah, variable integer. Cool. Okay. So then, that all looks good. And then we have what, squeeze, right?
Yeah. That will be very similar. One thing, scalar shapes, will they work?
What do you mean?
We represent it as like a tuple for the an empty tuple. So if it's a scalar.
Yeah, I guess we should have a dot empty class method maybe on the shape or something.
Okay.
It's a little,
Because I also I noticed that's something that it was not obvious to me how to do it. That's why I started playing with the tuple object.
I just didn't.
I wanted to.
Yeah. Or actually, yeah, that's fine. Cool.
So this is the same, I guess, then? Let's say for now the squeeze can also only be one axis.
Yeah, that seems good.
And that's it, because we have the multiplication.
And then, that seems good. And then I think for like our rule, we'll need to look up the shape. Like we'll need to look up the dimensions and maybe get an index from the shape. So we might want to implement like a get item for type shape that returns back an int. And it could just take a that seems good. You could just have it take a symbolic id too. Kind of just get in the habit of like just doing everything symbolically, and then get item 2 more underscores after it, the name.
Nice.
And we could also add a length if we want. I don't know if we'll need that, but that'll be like, or the dimensionality, whatever you want to call it.
That's nice. I want to add it, maybe if not for now.
It can't be the thunder length though, because I think that has to be a Python int.
Maybe.
Unfortunately.
That's another messy thing we do.
And you can even, go ahead.
No, that's fine.
I was gonna say you can make it a property too if you want, just for simplicity.
Is that an advantage?
Just when you call it, you don't have to write parentheses.
Okay.
You still put self in there,
Okay,
but
so
just when you call it.
Did I make it a static method?
No, that's good. That's because it'll just be it. Yeah. Okay, cool. Now maybe I feel like what might be fun is to try to write the rule first, and then we can, like the rewrite rule first, and then we can add more logic we'll need to like implement it, but maybe starting with that.
Okay.
So
what way do you like to write more?
Yeah.
So what's the way? I see there's alternative.
Yeah, I do the one with the function because you don't have to write the names of the variables once. So you do at egraph.register. Yeah, and then you make a function that it doesn't matter the names. So I usually make it private, but or call it like rules, array rules, or whatever you want to call it. It doesn't matter. It's just, yeah, whatever. And then you put all your args are just the variables you want to use. So like
an X,
yeah, stuff like that.
And we want
we can start writing it too and add more because sometimes it gets a little confusing.
Okay.
And then we just so
it's the yield,
ahead.
right?
Yeah.
Or is it yield?
Yeah.
There's a rewriting, right?
Yeah, rewrite. Yeah.
By the way, are these rewrites commutative or they only work?
No, there aren't. There's a by rewrite function that just adds both sides or both directions. But
okay.
Yeah, and so like so you want to do yield. Oh yeah.
Say sorry.
No, you can start just writing basically the case we want. So the sum of x times y, where the axis is. So yeah, the axis, just do I here probably because you want to keep this symbolic, right?
Yeah. Can I have quarks? Not that I'm going to use them because we
you can add yeah, you can use quarks. Yep.
Okay. This would be an in.
Yep, exactly.
Then there's going to be a condition is with a comma or something.
Yeah, right now the condition's on the second side, which is kind of silly. It's after the yeah, that's how they did it in Egglog. I should probably switch it to after the but yeah, it's after the two.
So I say what I want, one more
and then you put any conditions there. Yeah.
Okay.
Yeah, there you go.
All right. So then I would like to write this as x at sum x is equals I times squeeze y x is equals y. Given shape of y.
So you could just do so what we'll add is to the tensor we'll add a shape property as well. So then you can just do like x.shape or whatever.
Okay. Would that be a property? No.
Yeah.
It would be a oops. It should give back a type shape, right? Okay. This is where later on it might be different if you are working about type shapes or symbolic shapes. But for now, everything is a type shape. Okay, so this would be, and this is already an if, right? No, equality.
Yep. Yeah, no, it's already an if. So yeah, so you want to say, what are you trying to say? That the x. So
I want to say that y dot shape, and this already is a get method I equals 1. And I don't know if we added that possibility already.
And for the equal, it's like the rewrite where you close the parentheses on the first thing and then you do .2. So you say equal of, and that's just so that it can be type safe, because otherwise you can't make it type safe. And 1 should be like int of 1. The symbolic. Yep. Yeah.
Is this it?
That's it.
So it should work.
Well, it won't work because we'll need to define more stuff. But I mean, it'll because right now, for example, the things that aren't defined are the dot shape won't return anything, right? And indexing on the shape won't return anything. So once we define those things, then I think it should work.
Okay. So I need more rules. Everything is rule,
Yes.
right?
Yep.
Okay. So what should I do first? You said I have to do the dot shape to have a meaning, right? If it's a tensor dot shape.
Yeah.
Okay. Then I have to say how I created a tensor, right?
Exactly. Yeah.
So that would be, we passed it the shape, right? So I need a new argument.
Yeah.
Shape equals shape.
And we'll need a
name.
Yeah, you'll need to give it. You could just pass in another string, so you use this another variable.
Like this?
Yeah, exactly.
I cannot do it. I don't want to do it.
Yeah, because you want it for anything, right? It's just capital string. Yep. Like that.
This one I didn't need to define.
Yes.
Okay.
Not the string like, just the string. Sorry. In this place, it's the capital. Yeah, that one. Thanks.
Why is it complaining to me? Because
it's lowercase tensor. That should be.
Okay, so if I have a tensor with a name, shape, and I call the shape.
It's a property, so you don't
okay.
Yeah.
I want to make it a
method. You can make it a method.
No, because it's a static shape. Yeah. Okay. Just for now, because this will. So static shape, then it gets written to shape, right? Something like that.
Yeah.
Okay. What other rule do I need?
You need
of a shape, right?
You need the indexing of the shape. Yeah.
How do you usually do this? From the more general to the more specific? Do you have a?
Yeah. I don't have any kind of rigorous method, I guess. This is
shape accepted value. So I'm gonna need an E64. Don't I have that? Can I use this idea?
Yeah.
Shape.
So it'll be shape is oh yeah. So shape is that's right. Or shape, is it called something else? Tensor shape or no, shape type shape?
I'll get better names later. Type shape. Hi J, I'm gonna need a J.
So this one is like, hey, you're just using the constructor.
So I don't need
that one is only should be indexed by 0, right? Like type shape of I indexed by 0 should give you I.
Yes. Okay. Right now we only allowed that. Okay. 2I. So I don't need a J? Is that what you're saying? Or did I?
Well, then if we want to cover the shape, I guess in this case we only have if we want to cover the shape with more elements, we can add a rewrite for the addition. So like let's see how I do it here. Yeah, so I kind of do it recursively. So I say like rewrite like tuple shape of I plus or type shape, whatever it's of I plus another type shape plus or just like keep it abstract here, so just like a type shape itself, so just like a shape.
I don't
So
know.
it kind of like it's like a recursive definition where like just the shape like instead of plus type shape, it's just the shape variable.
This?
No, like type shape of I plus.
Okay. Plus.
Exactly. Yeah. Shape.
Shape. Okay.
Yeah.
Right. So if we have two type shapes, then what do we want to do with this?
And you want to define indexing on it. So basically the way to think about it is like if for every operation you have, you want to define it on all the possible constructors in some manner so that it resolves.
Is this what I want to do?
Yeah.
So if I'm adding two type shapes, J and what should I rewrite?
I think you need one more parentheses around all this stuff. Yeah. Yeah. Yeah.
And what should that be?
So if J is 0, right, that'll be I. If J is
covered by this, or we need to also, is that already covered by this case?
No, because it's calling indexing on the addition operator. So it's like, oh, that's not the same as calling it on.
All right. So this if J is 0, right?
Yep. Yeah. And
okay.
And the equal has to do the 2 thing, equal J to. Yeah. And that seems right. So yeah, because if J is 0, you're just. Yeah.
Yes. Well, we might be doing left to right, but
yeah.
we need a case. Do we need a case for the non-base case?
Yeah, when it's greater than 0. So you could say
do you have a GT?
There's so I would do here there's a greater than on the int64 base type that returns like a we call it a unit type, which is basically like a true false. So instead of saying of J here, you could do of int like in your in the rewrite, in the left hand side of the rewrite, when it's saying like plus shape of J, instead of saying J, say like int of some other variable. You could make that something else. I don't know.
What type does it need to be?
I64.
Okay, it has already to be a base. Okay. Yeah, sure.
It's lowercase I64. Yeah. So maybe call it.
Okay, I cannot do that.
And I sometimes do an underscore at the end. I don't know. Yeah.
Or I could implement a greater than in my
exactly.
basic.
Or you could do that.
Would that be hard?
No, we could implement that.
So that's. Can I use the Python one?
Yeah. But then I would have this return a bool, like well, I mean, you could have it return a, yeah, I would have. So then I would make another class called a bool, like an abstract boolean.
We cannot treat integers as booleans.
I guess you could.
An integer of 0 and an integer of 1.
That's true. Yeah.
Okay. But you are seeing something there that already it's going to need.
But maybe, I don't know, maybe for now, let's just not do the greater than on here, just so that we can always add it later.
Fair enough. So you were saying here, right?
Yeah, so that's great. And then just say equal to, yeah, exactly. And then that changes to, right, the shape of I minus 1, like shape indexed by I minus 1, because you're,
okay.
Yeah, you know.
Okay. Shape, because I already defined that.
Yeah.
I64 minus 1, right?
Yeah. Yeah. And then the conditional is you can just do I64 greater than 0.
This doesn't, not.
Yeah. Yeah. No, it's just you can use that. Yeah. Yeah.
Okay, perfect.
And in the shape, it has to be indexed by a int. So you have to wrap in your right-hand side of the rule, you have to wrap that all in an int. Yeah.
Okay. So here we use the integer types. Okay. Logic.
Yeah. Oh, also, I realize in this rule above, you don't have to do this equal to j. You could just say indexed by int 0 and just put that in the left-hand side instead of having this equal j to int 0. Just say, yeah, and replace j on the left-hand side with int 0.
So do I copy the whole expression and I say 0 instead
No,
of
just
j?
like, yeah. I mean, you can just edit j there to be int 0. I'm just saying, like, sorry. It was just like, we didn't need to.
Okay, not, she meant just this.
Exactly, like that. Yeah, and then that can just be I.
Okay.
Just so it's a little simpler.
Right. Yeah.
Yeah, if we can, yeah.
Tell me.
No, it's just there's a kind of an upstream issue where if we could implement like user-defined parametric types, then I could just write a tuple type, and then you could write tuple of int, or something, and it would have all these rules defined. So yeah, just another data point that might be useful, because these kind of rules are not that fun to write, and you just have to repeat them all the time.
Okay, so do you have all the building blocks?
I think so. We can try it and see what happens.
Okay. No, it's not. Didn't like this because what did I mess up?
Rewrite.
This should be int 0?
Yes. Yeah.
Are you calling like MyPy and then, or just Python?
I have my own type. I have to know the types of everything statically, basically. Yeah.
Are you introspecting bytecode?
No, I just look at the signatures, and I have my own basically.
Okay, so the signatures
type
are
analysis.
Given dynamically at runtime. Okay.
Yeah. I think actually we need one more thing. Well, actually, we can try it now. Why don't we try it now and we'll see.
Let's see how it goes miserably.
We can see how it works. Yeah.
See, do we use this let?
Sure.
Or is there a better one?
That's fine too. Yeah, I usually just do egraph.register, and then I just pass in an expression, and that adds it to the egraph. So you can make up your expression first, like
okay,
whatever it is.
Okay, so let's create our expression. So it's a sum. Now I need to create variables, right?
Yep.
So our x, well, yeah, okay, let's go like that. So I'm gonna need a sum of x times y, x is equals 0. What is a small sum, I guess? Oops, maybe I should have given. It's a dot sum. No,
I know it's a function.
I overrode the built-in.
I know. I realized that.
Okay.
That's okay. Whatever.
Well,
but yeah, I guess you can change it. Yeah.
It's lost. I'm not gonna restart it one time. So x, y axis. Okay, so I need x to be something. I need y to be something. So x should be
the other.
Sir?
Yeah. Well, we could draw it like this first. I'm sure.
Tell
Go
me.
ahead. There's just ways you can write conversions, so you don't have to always write int. Like here, you need to write axis equals 0. You need to write axis equals int 0.
Let's do it clean. Yeah.
Yeah.
So
Do it this.
x.
And like, yeah, that's fine. Yep, that's string like. Yep, and then this shape.
I'm going to create a separate type shape. Okay, and here I'm going to have to do an addition, right, to get my fancy shape.
Yeah.
So this would be int. Here is where I can have the. Was it a none, or did we get rid of that? No, we give it
a var. Yeah.
Okay, so x d 0.
Yeah, exactly.
X, we didn't know anything, right? It's none. Yeah, y is the one that has a fixed one.
Yeah.
X d1. Okay. Good, correct?
That looks good.
Just complain to me about something.
You need another parentheses? Yeah.
It color codes them? Okay.
Fancy.
And let's do the y. Y equals, there's a bit of sign. Except here is an int of 1. And could I, yeah, probably this I would make it a global variable at some point, whatever. Y. Okay. And now I register the expression. Do I give it a name?
No, you can just register it.
Okay, so first bug report, or not yet, because TypeShape doesn't have a method var. Yeah, it doesn't. It's not supposed to. Okay. Not the first bug report yet. Now I messed up the parentheses for sure. Let's break.
Oh yeah. I should add that.
So what did I mess up?
Yeah, that. Yeah. Yeah, if you have a, I guess that Colab doesn't do MyPy.
Yeah, didn't sure. Okay.
And I think the same. Yeah, the same with that one where. Yeah.
Yeah, definitely broken.
Yeah.
Much more readable. I could just have made it variables. Okay. Keyword argument shape. Maybe I call it static shape, probably. No. Can I not pass quarks?
You should be able to. Tensor shape. Yeah, that looks right. Name and shape.
Does it not like to have arguments with that?
It should. Well, I've definitely used keyword args before. Oh, is tensor the right? That's that's the right thing, right? Yeah, class. Yeah. Maybe try it without the keyword, see what happens. It's very odd though.
Yeah. That's it. Okay, so that's my first bug report. I thought it would be something more fun, but no, it's this. That's okay, we need squarks. And now, can we register? It was the same path as before. All right, we did it. So the first issue is this fails. Oh, it doesn't. Okay, you fixed it. I know it's not. I need to install this separately. I think it's not in the requirements.
Oh. Yeah, I put it. I didn't want to require Jupyter stuff, but I'll maybe make it as like I don't know what the best way to do that is.
Okay, but then it should fail nicely, I guess, if it doesn't.
If it doesn't have it, yeah.
Oh boy, this looks already beautiful. It's funny you need the init operation. Okay.
Not that's makes it less beautiful.
Okay, we have. I like the order it shows. Because it cares that it's the second argument. Yeah. Okay.
Yeah.
It doesn't know yet that it doesn't matter. Didn't I write that rule? No, just a.
Oh, and we haven't run any rules yet. So
I know.
yeah.
So what should I do? So the way I was doing. Well, do I just run?
Yeah, you could pass in some number, or you can try to use like a schedule to run it till saturation. But you could just pass in like 100 or something, or 1.
All right. Okay, definitely didn't get the addition because we are still multiplying.
Yeah,
Did
so
we
I think
did we do the rule actually?
yeah, we did. So I think the issue with the rule is that it's
do we have a rule for this? To know something is equal?
This is kind of confusing. So the equality, it's checking if this is equal to that, but it doesn't add this to the graph, right? It's just saying, hey, are these things already equal? But in the graph, there's no dot static. There's no dot static shape indexed by I on this operator. So what we'll have to do is add. It's kind of confusing, I would say. But what we can do is add another rule that basically says, hey, whenever you see sum of x times y, axis equals I, try indexing the shape by I. Like add that to the graph, that operation, so that it can then be evaluated, if that makes sense.
Okay, let's see.
So, and this we'll need to use the more advanced, I think. Yeah, because we're not rewriting this expression. We're just saying, hey, whenever I see this expression, add this other expression to the graph, right? So that's like a more complicated kind of rule. So you have to use this thing called rule instead of rewrite. And this is like the more general form. Just rule, yeah.
Okay.
And this is like what rewrites are actually converted into rules under the covers. So this is kind of like the more complicated. So here we're gonna say like, yeah, all these facts. So the facts are like equality or whatever. So we'll say like, hey, if I have some, say like equal, let's say I have some variable z. So z is equal to sum of x times y, axis equals I. Like you can just copy that. Equal, it's equal z and then 2, sorry. Equal z.
Yeah.
Close parentheses 2.
So we need to introduce these in the graph, otherwise we cannot reason about it.
Yeah. So then you can close that whole parentheses after rule 2.
Yeah.
So these are all the facts. It's like, okay, once all these facts are true, run this. So you say rule, and then you do dot then at the end, similar to the rewrite. Yep. And so then we pass in actions, which are actions to take. So then we can just say, as an action, add this to the graph. So you can just copy the y.static shape I. Yeah.
And they just puts it like in the graph as a new variable.
Yeah, it adds it to the graph, and then rewrite rules can run on it. So then our above rules will start running, like the dot static shape will run.
Cool. So in PyTensor, we do these with what we call features. When we writing, so there's going to be a feature that has, you can add the feature to the graph, which would be a shape feature, and then allows you to query. The rewrite then can query this feature to find if like two variables have identical shape, which is another of these things we don't really like. Because again, we are like, basically we have like, we don't have something that can reason about everything with the same kind of objects.
Exactly. And this was something that was added in Egglog and wasn't in the previous egg version. It's like multi-matching rules and such. So. Okay, so we can just try running this. If we rerun this cell, this is something that I haven't fixed. It'll try to redefine the squeeze function, and it will break because it'll say there's already a squeeze function defined. So you can either recreate it, like
I have to. Okay.
Recreate the e-graph, or I don't know.
Let's recreate.
What? Yeah. I guess. Oh no,
Right.
it's fine. It'll be in there.
I'm always running everything from scratch.
Okay, good.
Probably I just expect them to express not more 0.
Runtime. Equal to.
I don't have the Z also to start.
Oh,
with, so
Z. Yeah, that's. Oh, I think Z was probably defined in your outer scope.
I tried to multiply. Okay, maybe it was a PyTensor error.
Exactly. Okay.
Okay. So now it's gonna introduce.
Let's see if it works.
Let me run once just to see that show up. All right.
Okay, so there's the Now it's doing the get item, right? And the shape.
Cool. Okay, let me just see if I make sense what we did. If x times y, we are just adding these the graph so that then we can access it in this rewrite. So in theory, we would want to add all the static shapes in the graph, and then we could also reason about them, like find equivalence, like I was saying. Like if x and y are being added, then we can say the dimensions are the same.
Yeah.
Stuff like that.
I mean, you basically need it whenever you have a conditional in a rewrite rule. You need to make sure that everything in the conditional is in the graph, so it'll.
No, that's sweet. Because many rewrites we actually like to evaluate the cost of like an operation. It matters like the shape, and it's nice if you could do some shaping for it as well. Okay. Wait, getting a ghost from Discord. Okay. In 2 types. Perfect. Okay, so now this should work. Is there a nice, more compact? Well, I guess I could zoom out.
There is a more compact view. A little bit more compact. So if you call, basically it'll just wrap up your. Anyway, it's fine.
Yeah, let's see how ugly it's gonna get. Well, I guess I can just keep running the same. Okay, now you have something happened. Did it? So I'm looking for. I should have at some point a sum times a multiplication. We're not there yet.
Oh, and you can also, there's a way to.
Tell me, is there a trick I should?
There's a dot saturate method which will visualize.
Yeah, but that was very laggy for me.
I know maybe it won't work that well. Yeah, you're right. Yeah.
Let's see. And it's a bit buggy. Sometimes it has a control, sometimes it goes away.
Yeah, so maybe it's not worth it. You can just go back to what you're doing.
So okay, let's run it. Tell me.
No, that's it.
How are you in terms of time? Are you good?
I'm good, yeah.
Okay.
Doing something.
10 times should be enough, right? We don't have that.
Yeah.
Okay, so the sum is already equivalent to a multiplication, or to 2 different multiplications. Nice.
Oh, because of associativity. Yeah.
Sorry, I should have taken that part. Put it later.
Yeah.
Let's keep our lives easy. I just love that part.
I know. Okay, that's smaller.
Okay, so sum is already equivalent to a multiplication of a squeeze of. Squeeze at 2 arguments. Okay, 0 argument and y. And I think this is it, right?
Yeah. And you can also do extract multiple, and you can see It's going to egraph dot I think it's extract multiple, and pass in,
And do I pass the expression I want to
expression
extract,
and the number, the maximum number. So you could just say whatever. There's only 2, so. Oh, well, that's not very helpful. You could pass in maybe more than 2 because it's getting 2 different sums with like maybe just. Oh, it's
no,
only
this is
getting
all it
those.
has.
It's not even. Yeah, I find that that thing doesn't work that well. So the other thing you can do to check is you can just do ef.check, and you can say, is this equal to that?
Yeah, that's the one I usually use.
That's probably the safer way to do it.
So then I should write it. Okay, I can write the 1x. And I can redefine it again, right?
Yeah. It doesn't matter. Yeah.
Does it take 2 arguments, or does it take 2?
It takes a fact, so it takes the equal thing, equal. Yeah. 2.
Okay. So we want it to be equal to times y squeeze.
Hey, it's weird. The keyword args are working here.
You surprised?
Well, they were. So I'm still confused why they weren't working above. Oh well.
I'm just missing it.
I think you need one more. Yeah.
This one is self-defined. This could be self-defined. It's this.
No, it just it does it in Rust, so it just it'll panic if it's not true.
Okay. Is there okay, yeah, that's not important now. Okay, so I think this gives a nice picture. Okay, yeah. So things I have to think about is when we introduce this stuff, we can introduce static type shapes. Those are fine, they're always available. Or we can introduce shape operations, which can be symbolically. So we might find, for instance, it's worth to compute the shape of something that's not known, and then based on that decide to go left or right, for instance. That's
my hunch is that you might be able to get away with using the same shape attribute for static and dynamic, but just sometimes compute it and sometimes not.
Okay, so I guess if I wanted to, this is pretty awesome. So okay, let me just do the skeptical. No, I wanted that. Well, I will do that. Okay, let's make sure.
Make sure it doesn't.
Okay. Did find something? Let's see. So if this is 1, this shouldn't be equivalent. Is it gonna raise or return false?
It's fine. You can just run it. It'll hopefully. Well, it is doing some kind of replacement. I'm curious.
Yeah, we'll see what if that's doing something weird. But so this shouldn't. I think this was the not equivalent case, right? Let's just see what I wrote at the not equivalent.
Axis equals.
Axis 1 and the squeezing the 0.
You can.
I don't know why. I can squeeze the 1. Okay, the reason I didn't do it is that this would be like it will run already. It would raise already eagerly because it knows you can squeeze something that's not in fact with 1. But that's okay. So I can check if it's not equivalent to this. I know it's not going to be because it never tries to transfer to 0. But maybe then we can check what.
Yeah, let's look at the graph. What did it do?
So you think the sum is the same as a multiplication?
Yeah, so that doesn't seem right.
Okay, let me see first if I wrote it correctly. It might not know that if this is not known.
No, it shouldn't be equal.
Wait. First I have an error here.
Oh yeah, wait, it's saying, so here you'll see in the get item, it's equal to 1.
Maybe we
It's
have
saying that
a bug in the get item. First, oh wait, let me restart the graph, sorry.
Yeah.
This is already. Okay, so that's fine. We don't have any get item, right? Now we run once.
And that's saying, let's see, it's getting 1 of that shape, right? And the shape is, should be, that should give y, it should give that y dim 1, right? Result?
Where do you see it's asking for the first?
It's asking for the first, or index 1, yeah. Yeah.
Where do you see the index 1?
Well, this 1 here.
The one in the bottom?
Yeah.
So you're still reading the, yeah, that's something I have to get used to. I'm used to the arrows in the direction. I'm used to 1 is the argument that goes into the get item. And the other argument that goes into the get item would be a static shape. So I'm always reversing this in my mind. Okay.
Oh gosh.
1 get item. I mean, it's doing it that, but it didn't figure out anything.
It hasn't figured it out yet.
And the static shape, what goes into static shape is tensor init. Yeah, this would be nice if this was a dot. Wouldn't be possible?
It would be nice. The problem is it kind of like converts it in Egglog. It's you can't use dots in your names because it's like a Lisp-like language, and I should work on.
Could it be an access or something?
No, I mean the real there's a fix. Yes. That's the short answer. Yes, we can make it a dot. Is the short answer.
That's okay. I'll make everything a function, and then it won't. This won't happen.
No,
a
it's
static
good.
shape will be a function. Okay. Okay. So this is fine. Let's run it again. Is it finding anything yet? Get item. It's adding shapes already. That's good. Okay. Yeah, this is the first shape. Maybe we are missing left and right when we add the shapes or something like that. Okay, we add the shape.
Yeah.
Y dim 1 makes sense.
Okay.
Now it's still getting the first item. It only knows to get the first time. Okay. So this changed meaning from before, right?
No, I think it's the same. The other thing you can pass in if you upgrade your egraph dependency, maybe there's the default for the visualizer changes to make it a little bit more compact. But actually, you could even just pass it in. So either way, there's a keyword arg you could pass into the display to make it a little more compact. So if you do dot display, or just do egraph dot display, and then if you do n inline leaves, this is very.
Inline.
I just put n underscore inline underscore leaves equals 2, for example.
Okay.
So then it like smooshes basically any constants up. I don't know if it's more or less helpful, but you can kind of.
Good. So it gets rid of these annoying units, is that it?
It basically takes every node that's just a single element and pushes it to its parents, so you can kind of see it more. It does it twice with the 2, so if you could also try it with 1, it'll just do it once.
Okay. It's nice.
See, so kind of like remove
Like
some
that.
nodes.
Okay, so now now we have only
It's a little bit easier.
objects, but not the initializer of the objects. Okay.
Yeah.
Okay, so let's run it. I didn't save the previous one. Okay. Extend. We need to add. That's good.
So the get item is moved up, like it's
Yeah. So now we have 2 get items.
Yeah, that should be right. Yeah. Yeah.
So this get item, which takes as input the dimension 1 and
yes,
the
0
index is equivalent to, and I cannot follow these lines.
Yeah, it's equivalent to this. It's the recursive case, I think. So it took the right-hand side of the add and said index 0 into it instead of the full add and index 1.
Okay. So you think it's correct so far?
I think so. Yeah. Yeah, so that looks right. There's int var. You can see it in the equivalence class. Ydim1 is equivalent to the get item.
Get item 1.
Yeah.
Int 1. Okay, yeah. The first one is 1. The second we didn't try to figure out, right?
What do you mean?
Okay, sorry. Type shape get item, type shape get item. 1, 1. And the 0, the Ydim 0 doesn't come anywhere.
The 0, so
because it was we made it an integer.
Yeah, the 0 is the indexing. Just it was indexing just into the smaller type shape.
Okay, so now it seems to be working. It didn't find sum is equivalent. Maybe it was just I didn't reset it properly after I changed the expression.
That seems like it's working.
Yeah, I did this, but I didn't reset the graph, so I shouldn't have done this. A separate cell.
Yeah.
Okay, all right. Cool. Let's make sure this is still correct. Yeah, I think this is great. So the last thing I would like to ask you is sure, do that. Nice, sweet. Is how would I represent operations the way they are defined in PyTensor? Because they're not defined as functions, they are defined as classes with some fixed properties or something like that. I don't know.
Yeah, I think this is the biggest. I think the biggest difference is I think that in this case, I think you would define them as a function, and any properties would just be arguments, basically.
I'm thinking like programmatically, right? Because what I have is PyTensor operators, which are classes that tell me what this computation means. I don't have a trivial way of converting that to a function. I guess I could make a partial. Yeah, so I guess the challenge would be
the question is, you're kind of asking like, how would you map the existing PyTensor structure into this form and back, maybe?
Or if so, this would not be my intuitive way if I was trying to just convert PyTensor stuff into this. I would think of operators as classes.
Yeah.
Or a function that takes a class, an operator class as the first argument or whatever.
Yeah, that's what I would do. Like if you had a binary op or just a generic op, and maybe in this case binary op to just be specific about the number of args or something. Like the first argument would be a class that was like op type, right? And yeah, so like we could convert like you could convert multiplication here into a binary op.
Yeah.
function, something like that.
Okay, let me just see how ugly does it get if I do that. So op is an expression.
Yeah.
And
you can make, there's a couple ways to do like kind of like enums or whatever. So instead of having to do methods, you can do them class vars, or you can do constants. So there's two options basically. They're the same under the hood. It's just how you want to write it in Python. So if you want to write like op.sum or op.add, right? You could make that a class var, or you could just make a sum constant global. But like so if in the body of op, instead of having an init, like if you write just sum, or like I guess in this case it'd be add, right? Or multiply or something. Multiply.
Yeah, let's do the multiply.
Well, just do mul.
All of them actually, yeah.
Mul.
Or not?
No, not def, just mul.
Just okay.
Yeah, and then colon. You just write the type, so you just do colon, and then you use the built-in Python typing class var. Like it's from the typing module. It's class var.
Is that imported by?
No,
Egglog?
I don't think so. It's just from typing import class var.
I'm not familiar with that. Beast.
Yeah.
Class var. All right.
Yeah.
Class var.
And then you say class var. Yep. And then you in the brackets you say the type. Like it's like a generic type, so you use the brackets. Yeah, and you say like op.
Okay. Tell us to
So
do
this
that.
is saying
Anything? No. Okay.
That's it.
Okay, so let me show why, besides the fact that everything is an op. So I'm thinking of stuff like how we do indexing. The way we do indexing, well, maybe I have a vector. No, I overwrote Texas. Let me get it. It's because the multiplication addition, yeah, okay, those are not so interesting.
Like you're thinking like broadcasting and stuff like that? No.
I'm really just thinking how we define that in the PyTensor. And now I would want the rewrite. So the rewrite, the way I would like it is I can say, so the way I would have a, like distinguish, let's say a slicing from like a.
Yes, yeah, all the different types of indexing. Yeah.
The way that I would write it in PyTensor nowadays, we have some like pattern matching thing. The way you do it would be, you'd say, you would have to, yeah, you basically include the op initialization as part of your like pattern matching. So this would be a, because we don't have like everything is a subtensor op, but then it's an instance of that based on these properties that are fixed. So for instance, if it's an indexing, it would be or something like that, versus if it's a slice, it takes a slice of scalar type, and then this would be a start none. Okay. So if I wanted, the rule would be this op applied on x, the index is 0, would be something like, I don't know, maybe it would be the type. So let's say shape is an argument itself. Yeah, something like that. Then I could have a rule that, maybe not shape, let's say ending, make our lives easier. That would be x and b minus 1, stuff like that. Okay.
Yep.
Or more interesting rule, so this one probably would work for any kind of subtensor op, as long as we have a single one. If you have a double slice, then it's the same op, but then there are, for instance, 2 slices. If you're skipping something, there's a none type. So I don't know. It's the way we define the function is a bit weird, maybe.
Yeah. So like if you're saying basically, let's say I do some indexing and you want to compute the dimensions after indexing. That's kind of like what you're saying in that.
Or even that, okay, maybe we can do that. I don't know if you have time. So the rewrite, that the other one that I mentioned was the one if you index on exp x0, then you could just do x0, right?
Yeah. Yep.
That in PyTensor, the way it looks like, and this one we have, so we have an x, we have an x, look at that. X, y, I can show you the before and after. This is the after. I'm going to put the types, which are a bit ugly, but yeah, just the types. Yeah. So let's see if this makes sense. Okay, then let's complete that. Okay. Okay, yeah. So
yeah,
the way we represent is, so the subtensor still takes as input an index and the thing, but this subclass is a specific subclass that was already known to.
Yeah.
It's going to be a subtensor operation that takes one input and it's going to be a scalar. If it was a slice, it's different. Then you can see that it would look like, okay, this is a subtensor instance that has something like that.
Yeah. So this is, I think like this could just be like the get item, basically, of the, like we could try to implement this, but basically it's just like the get item of the tensor class. Could be that op, I think. And then the question is, how do you differentiate between all the different types you'd pass in, like slices versus indices?
Yeah. So I would, I think the more manageable way would be a function that always takes an op as the first argument. And this op, then I can, so I'm just thinking how to do this programmatically. Then this op, I can define whatever it's needed to instantiate the op, and then I pass the two other arguments. So I would try to do as little as possible, like methods. Yeah, so I would, I would like to represent like both of the tensor operation.
Most helpful if we had it, like another example where you're saying if two different things and what's the generalization maybe? You know, like, because obviously we could implement this rewrite trivially with what we have here, but yeah, if there's like, I don't know.
Does this example, you mean something more, is this example not enough?
Like, for example, to implement this rewrite of moving the indexing in to the exp, like we could do that. We could do that right now if you want. I mean, we just write an exp function and say whenever you're indexing an exp function, you know, swap those and rewrite.
Yeah, I guess what more interesting for me would be just to see if we can easily represent these in the way that I feel that I need to represent it to be able to use Egglog more generally in PyTensor. So it's not really the exp. It's represent, and we don't need to go to this example. So I would just like to represent then, and I think that's not too bad, right? So I want like to represent ops, and then have all the functions take op, and then my rules would always be. So I wouldn't really have a multiplication, maybe necessarily, or I mean, I don't know. So okay, the core case I would specify in the rule a multiplication is not something as nice as this, but would be a mul of an op, of an LMI's op whose scalar op is an addition, for instance.
You mean for this example, for our rewrite rule we wrote here? Or
okay, let's just do, we can just do that. Okay, so we have a mul is a
and we can maybe make an add too, just to.
Yes, and I would maybe the sum would already be nice because the axis, I would like the axis to be part of the op.
But like, for example, for mul, there's also an axis.
Not in this case, no. Mul is doesn't have an axis here. Some has.
Yeah, some has. So that's why I would say, like, I mean, if you have a collection of functions that all take the same kind of keyword args and behave in the same way besides like something, then yeah, you could make a op out of them, I guess. But it's just a question of generalization, how much you want to, you know,
because what
would be the repeated functionality between sum and add? Like, what is the common pieces, I guess, would be my question, between implementing the semantics of sum and the semantics of add.
I pass optional properties that are always like integers or strings. It's basically a class instance that identifies this operator that I want to not necessarily, some things I will want to reason about. So something will be axes. I will want to reason about those. Others will be meaningless, but that's all the things I have in PyTensor. I have these objects with properties, and I want to make rules on these objects. So I need to.
Yeah, I mean, maybe. I think this is the biggest change, I think, to going to a system like Egglog compared to most of the other rewrite systems, is that there aren't, you're switching from classes basically to functions, and classes are just used for types. So classes are just, you only have classes if you want to represent a certain type with certain operators on it.
Okay, so the op can be a function itself, although you have the issue that I cannot have like.
Well, basically, the only reason you have an op, like I would, like for example, I might make a bin op, a binary op class, and then say a binary op function like def bin op that takes in a tensor, takes an op description, and calls it, because maybe there's a lot of shared functionality between all the binary ops. Like they all do broadcasting, and then they all,
so that's what I was saying with the LMYs that we have.
Yes, all the element-wise.
Everything that's LMYs has the same like broadcasting rules, and it's just defined by a scalar op.
Yes. Yeah. So I think that does make sense to have like a type of ops, and then it's just a way to reuse basically a bunch of rules between different operations. But
so it's just that, like, if I put, so we can already, did I show the pattern rewriter? No, but I can. Okay. If I wanted to write our rule in a more like rule, like our rewrite the sum in the most like rewrite
most generic way, or
the most like symbolic, like the most similar to this, to Egglog, and not imperative, like check this, check that, would be something like we have this language. I'm going to use exactly what we have. So I actually defined the op. That's not so pretty. Do I? No, I don't need to. Yeah, sure. So sum.
I think I might need to go take a break for a second, if that's okay.
Okay. Yeah, that's fine.
But I'm down to keep working
maybe
on
this is a good time.
But
yeah,
either way, or we could pause and come back.
So let me just say that, first of all, this has been super really great. Some of these things
fun.
I'm gonna have to wrap my mind, like this recursive stuff really reminds me of what is it, like lambda calculus or something, like because deriving everything from like addition of, I don't know, truths and falses.
Exactly.
But it's a really fun exercise though.
Yeah.
Yeah. I think. So I was just mucking around, and I was writing this in the way that if we could make rewrites a bit more similar to this, would be really powerful for us. So it just makes it very ugly. I started commenting this, how I would write this rule in a comment, and it was exactly the same code as this. So that's beautiful. This one is not as beautiful.
Yeah.
Let's just finish it. Maybe yes. This would be well, we call this a dim shuffle, so let's just even worse. The thing would be, we are taking it away, so it's just 0. However, look at this.
Yeah.
Yes, yeah, this is fine. Variables can be variables like this. That's not too bad. This can be the same. This I was already in it. Yeah.
Yeah.
I don't know.
Yeah.
Does this make sense to you? I mean, not that it's gonna work, but you kind of see where I'm coming from. So for us, a sum is a more general, just a reduce. It's can be anything that's like commutative. I don't know. They call it car reduce, commutative, associative, whatever. So any of there's a couple of days. Like sum is this, maximum is greater, minimum is smaller. Binary ops. That's how we define it. Now, this rule for this one doesn't really matter because this rule is specific to an addition. But for some other, this might not matter. Like any reduce op, whatever it is, would work.
Yeah.
Yeah.
That makes sense. And same with the element wise.
This one is specific for multiplication, but it could be something that it doesn't really matter what's there. It would work. And so I would like to be able to write rewrites at these two levels of abstractions, basically.
Yeah, that makes sense. So I think we're pretty close to this. I think we can get something like this quite simply.
I mean,
yeah. So I think they'll be functions, but I think it'll be similar semantics. So so I think we'll just make a few changes here, and I think we'll be close, and then we can add the function. So like reduce op, if it takes in, so I see it's taking in the scalar.
Daxis.
Yeah, it's taking this. I see. Okay, so this reduce op. You could do it as this two-part. Just looking at this.
So
I see.
one option is everything
Yeah, that makes sense. Oh yeah, what were you gonna say?
So one way is that so this, I don't know if you support, like this would be a higher level function, right? But we can also just flatten everything.
No, yeah, no, actually I think if we want to do it as a class, we can. And in this case, we can implement this kind of functionality, even just this exact syntax, basically. I think will all work. Let's see, just looking at this. The only, yeah, that's fine.
So for me, it's not important that we implement it as a class. It's important I can work with these objects.
Yeah. No, I think that we can do it as a class. That makes sense. If you want to deal with them separately. Yeah.
We can try that. Or if you see an easier way, we can also try something else here.
No, that makes sense. We can implement this. And then it's just up to you which way you want to write it. So, and we can rewrite one or the other or whatever. So it all kind of ends up being similar. So like we could write a reduce. So I guess we can start with this. So we'll have a class for Yeah, we could just have it. Do you want to be able to use the same ops in reduce and what was the other one? Bin op or something? No, in what were the two names you had? You had reduce op and element-wise op.
Element-wise op.
Do you want to be able to use the same ops in both of them, or do you want to make sure that those are separate, or is it fine if they're?
You mean the fact that scalar here and here
yes, it's the same. Yeah. Okay. So either way, yeah, it's just a bin op basically, right? Yeah.
Yeah.
So yeah, if we want to we can even keep your spelling the same if we want. So we could just say, like for example, scalar mul op equals like above the rules. Like we can define these.
I can copy it here so that. Just comment.
Yeah, exactly. So we could define them as class vars, but if we don't want to, we don't have to. So we could just keep this op class, but just you could have no body basically. And then, yeah, I guess you'd have two. So you'd have maybe call this op type class, like because the instances of it will be like scalar or multiply. So then you could say like scalar add op equals egraph dot constant op type, egraph dot constant, and then I think you put the name again. Yeah, I think it's constant. Is that right? Yeah, constant.
Op type.
Yeah, the name. So the name will be scalar add op. You kind of double it.
Is the name comes first or the argument?
The name comes first, I think. Yeah.
Okay. Op type or a scalar add op?
Scalar add op.
Okay. This will identify it as being a unique.
Yeah. This is the same as like a function that takes no args and returns an op type, but it's just different syntax. So you could do that. Yeah, you could do the multiply one.
Yeah, these are kind of the most low-level building blocks. I mean, we have a distinction about being binary or not, but that's not important.
And then,
yes.
and then we want the reduce. Yeah, we can make that a class.
That's in the element, so that's more primitive for us. Yep. And that's a new class, right? That's what you're saying?
Yep. Because basically the way, yeah, it'll take an arg, right? I mean, you could actually call it and reduce takes one arg. Is that right?
Reduce takes two because.
Oh, two. Oh, it takes two args, but I mean, it's applied on one array.
Yeah. Yeah, you mean as an operation, yes. It takes
yeah, as an operator. So maybe you could have two kinds of, you could have a unary operator and a binary operator class.
Okay. Can that be defined at the scalar level?
You would
no, okay. Yeah, I see what you mean. Okay.
so it would,
yes. Would that be a separate class completely?
Yeah. It would be called unary op. And then it's in its body, basically, you could just implement a call, under call, that takes in a tensor and returns a tensor.
Okay.
And you have to put a name for the variable, second arg x or whatever, or something like no, like
yeah.
Yeah.
Okay.
And then you would define a reduce op as like a way to create a unary op, right? That takes in. So it would be either a function or a method or a class. It would either be a function or a class method on unary op. So either way, you could just make it a function, I guess. Yeah.
reduce up.
Yeah,
And this takes.
and so, yeah.
Well, it's not really an area up.
It takes the, I think it would take an op type. Yeah.
Yes, it returns a unary up. Is that it?
Yeah. Yeah.
Nice.
And it takes the access too, right?
Right. The access would be again that complication that we would have to make a
It'd just
tuple
be,
if we wanted more, but for now.
yeah, for now it'd just be the int. Yeah.
Okay.
And same with the element wise.
Yeah. And yeah, even for the scalar ops, maybe I would make them these silly functions. How did you call them?
The which ones?
The functions that take no arguments.
Oh, the unary, constants.
Yeah. Okay. Yeah. Makes sense. So LMY is okay. And takes. Well, can take anything.
Oh,
so here is where we might need
a binary op. Yeah.
Yeah, that also have to still. There's no, yeah. So in our case, we actually have stuff that accepts multiple. Okay, so we have LMIs with multiple inputs and multiple outputs. I just have to think how we would.
In this case, I think maybe just do 2 inputs and 1 output, 2 tensors. If we want multiple outputs, we'll have to do like make another class that is for like multiple outputs. They're not built in.
Is there no, like, there's a struggle here with tuples, no? Seems like something is missing that would behave like a tuple. Probably there's some fundamental reason for that, I guess. Yeah. Okay, so this is a, well, let's say that all our, I think in our case we only have multiplication, that's fine.
Yeah.
Okay, so are we done in terms of what we need to create?
Yeah.
Okay, so it's just that. So we have the squeeze.
Oh, and the squeeze op is
it's something different.
It's a unary op, I guess. Because you squeeze 1.
So the squeeze op is a pure op by itself.
Well, how do you define? So it's like squeeze op. I think you could have it.
Could I have a non-op? Or how
What
are
do
you
you
thinking?
mean? Just have it take an access, right? Just an access arg.
Yeah.
Squeeze op takes an access and returns a unary op.
Okay, one argument. We just take access. Okay. Right, so we're not intend to force ourselves to. Perfect. Okay.
Yeah.
So let me take this just a way. Everything else here shouldn't matter.
Even if you keep those, for example, like we could just rewrite sum and squeeze to be those other ones too. So
yeah, I was thinking so because this is going to be nicer to write. Some rewrites. Yeah. Some things that are not too esoteric, like addition. Yeah. Right. So you would have a rule that converts this ugly thing into a function of this ugly thing into a function of this.
Exactly. And you could do vice versa too.
Yeah, I like that. Cool, because then we can use rewrites that other people wrote and just apply them here, right? Yeah. Yeah, that's sweet. Okay, so then you say that, okay, does this already work?
I think that should.
Otherwise,
we'll need to do that same introduced. Yeah.
That's here, right?
We'll have to do that introduced static shape thing.
In this language, right?
Yeah, we'll have to switch it.
So this is a reduce of this equals I. Yeah. Okay. And if I have a commutative rewrite, then both of the shapes are introduced by just introducing the first, right?
If sorry,
If
what do you
I
mean?
had this rewrite,
then
then
that's
this
true. Then yes.
is both, right?
Yep.
Okay. Case. Surprised I don't need more parentheses. Is there?
I think you're missing the element-wise op scalar multiply op.
Well, actually, why are we doing it at the reduce up? Yeah, why are we doing it at the reduce up? Why aren't we doing it at the x times y?
What do you mean? Why not translate why not get the shape for every x times y? Is that what you mean?
Yeah, why did we introduce the shape?
I mean, you could say, hey, for every x times y, well, because you only want to get the shape at that axis. Well, it's getting the shape and then it's indexing by that axis, right?
Right. Okay, but I guess what I would want was just any operation. I just take the input and I introduce a static shape. But okay, we do this like this now.
Yeah.
But it would have worked the same way if this was just the mul, right? Because it doesn't matter where we introduced it.
Yeah, you could do x times y. Every time you see x times y, take the shape of x or something.
Yeah.
You could do that if you wanted.
Okay, I'm going to change the things. So now we have one more source of bug. Okay, let's go back. I have the mental picture that so that works. So this would be then that and minus up more scalar multiplication. Call it scalar mul up. Okay. X, Y. Yes. But now my rule is broken.
One more parentheses, I think.
Here, you reckon?
Yeah. Yeah.
Okay. Okay, so this is it. The graph now is off of okay. Sum. Where do I select?
Because in your expression, you're using the old at the bottom. At the last line, basically, in the expression. No, not in the rewrites, but in the.
But I also see a multiplication here.
Oh yeah, that's true.
So this is now minus up. And can I have like intermediate variables?
Sure. Yeah. Yeah. It's all.
Can I say that
all just
LMY
expressions.
is
Yeah.
I define them outside of the.
Either way, it doesn't matter. If you're just using it for rewrite rules, you could just define it in the function.
Perfect. Yeah, because this gets up really quickly. Scalar axis equals y. Yeah, so basically we lift the multiplication. No, otherwise doesn't have axis. Yes. Now these are the two arguments. Yeah, it's this, right? And there was a sum.
In your expression at the bottom.
When I define the expression. Yeah. So let me see if this equivalence without the expression. Sweet. Okay. Yes. Reduce. Perfect. So it's the same. Yeah. These I can see an immediate path then to play with these things. Yes. Come on. X is equals 0. Something like this. Now the graph is even more awful. Yes. Perfect. Let's see. Well, what should we see? What is the sum in our case? So should be the reduce up of the scalar addition. So is this the one that's going to be equivalent?
I think it'll be the call that's equivalent.
The call. Okay. Sounds like, yeah.
Yeah.
Because yeah, we had the unary sum, and now that's equivalent to the binary call on reduce up, yes, and on oops, I think that's more to the right, I guess. Squeeze, yes, yeah, like that. Okay, do you see any obvious? I mean, yeah, I hope this is not too ugly for you.
No, I think what's interesting is that you can write it both ways, and then you could write rewrites between them, and functionally it ends up being pretty similar in this case. But obviously, like in other cases, like you're saying, where you need to be generic over the op, and you could do that too.
Right. How would I do a rewrite where I don't care what is the thing that goes here? I just, this is a new variable type of
You just
type.
make a variable, yeah, op type and
Type.
and
Yeah, of type.
yeah.
Yeah, that makes sense. Yeah, this is perfect then. Cool.
Cool.
Yeah. All right, I'll play a bit. I'll write to you. This is great. The only annoying thing is the tuples, but we'll live with
Yeah,
that.
the tuples. Yeah.
Yeah, even for the arguments here, like if I have multiple axes, I'm gonna have to write the tuples
Exactly.
as
Yeah. And
either
if
I
you look
write
at,
all the permutations or I have to
yeah,
always do it in this addition way, no?
yeah, and that's if you look at the ND array implementation, a bunch of it is just dealing with tuples and also unions. Like if I want an int or a slice, right? Or an int or slice or tuple.
Right.
Right. So if you're curious how, like, you can look at that code. There's examples of like, yeah, for like indexing, right? Because there's so many options. The only other thing I feel like we didn't cover exactly was just conversions, but I think you don't need those, but that's just so that as a user, you don't have to write out all of the basically upcasting, you know, instead of having to write int I or whatever, you can just write I and you can register basically a way to upcast so that you don't.
So I can make the whatever the type shape
Yeah, like
accept
for
either
example,
an int 0
exactly. You could
or
just pass in. So like it's actually quite. So you could just, if you change that to 0, right? It won't work at the moment. But then if you go up to wherever our int is, yeah, this int class at the top.
so it can accept.
Yeah.
Well, it already accepts.
And then if you add a line after the int class is defined, so and just say you're calling this converter function.
Okay. Do I do it as a method or?
No, just like a top level. You're just calling converter as a top level function, and you're saying you can go from, in this case, I64 to int. So from I64, because there's already conversion from int to I64, the Python int, not your int, and you want to go to your int, and then there's the third argument is the function that does the conversion, And that function in this case is just the constructor, right? So you can just type int again, but you could have more advanced. So now you can always pass in an i64, and also you can always pass in a Python int because there's already a conversion from Python int to i64. So it's transitive.
And this is some kind of global dispatcher thing. That's why I don't need
Yeah, this is just in the Egglog. It's just for when you're passing stuff into functions, it can upcast automatically.
That's nice.
Yeah.
That's nice.
Yeah. That's handy. And so for that kind of thing, like with tuples, I have it upcasting. So at least when you're writing tuples, you don't have to write all the addition. You can just write a Python tuple of like 0, 1, 2, and it'll upcast it into the annoying representation. So as a user, you don't have to be stuck with the.
That's helpful.
Yeah.
Yeah. I have just two questions. One is how would you going about allowing arbitrary number of inputs and outputs?
Or
in our
like ops?
LMYs, our LMYs can take can have an arbitrary number of inputs and outputs.
What's like an example of that?
We have a variadic version of addition, for instance.
Oh, that adds any number of arrays.
Yeah.
So in this, I think how I do it now is basically have it like I have an array tuple or arrays or however you want to call it, a list of arrays and you'd say that you call it maybe instead of a binary op, you'd say variadic op, and it would, instead of taking an array, it would take an array tuple, basically. And with the conversion stuff, you could still pass in a normal array, and it would kind of upcast it to a tuple or something, or whatever.
The other place where it comes is like our loop operators have an arbitrary number of inputs, outputs, right?
Yeah, and so the same with the outputs. If like I had some functions that have, like for example, like the counts operator in NumPy like has multiple outputs.
Yeah.
So you just have like a class called like counts output, or if it's just like two integers, like tuple of ints, and then on that class you implement indexing to get each item, and you know, if that makes sense. So if it's a known length, like just 2 items, you just say like you don't need this whole generic list. You could just say like a list with two elements, make a type for that, and
right. Yeah. We always know already how many inputs and outputs we have.
Okay. Yeah.
Okay, but yeah, it's just things that gets a bit ugly. Okay. Yeah, I'm gonna have a lot of questions, but I'll write to you, I think.
Yeah, that sounds good. Yeah, feel free to write. This was fun. Yeah, and if feel free to also post online, or there's a Zulip and the GitHub too, but email's fine too. But that way, if other people have the same.
Yeah, that makes sense. I was just too shy.
No, I understand.
I'll do that. Now I think I have the building blocks.
Okay, cool.
Yeah,
this was fun. It's
okay, thanks a lot.
Cool to see that it's not totally insane. Yeah.
No. This but my issue was really like how to represent these
definitely
things, and now I have a good mapping from our ugly stuff to this.